A regression line is a line that passes through a scatter plot of data points while minimizing the difference between the actual values and the estimated value. Linear regression lines are used to model the relationship of how a dependent value, or the y-axis, changes in result of the independent value, which is the x-axis. The dependent variable determines whether the line is positive or negative. If the dependent values of the points increase while the independent value increases, then the regression line is positive. If the dependent value of the points decrease as the independent value increases, then the line will be negative. To create a regression line most accurate as possible, you must minimize the errors. Errors are the vertical discrepancy between the points on the scatter plot and the regression line's estimated value. Linear regression lines are expressed by the equation y hat is equal to b naught plus b1 multiplied by x. Y hat is the estimated value of y in a regression line. This is dependent on the x value and what we're trying to solve for. B naught is the y-intercept of the regression line, or in other words, the predicted y value when x is equal to 0. B1 is the slope of the line, and the x value is the inputted value, which is controlled. The first way to solve for this equation is by using the least square method. After obtaining a set of x and y values, you must solve for the mean of both sets of data. In this case, the mean for x will be 3 and the mean for y will be 5. It is important to note that all regression lines pass through the point where the mean of x and y will cross. So for this set of values, it will pass through the point 3, 5. Then you must subtract the averages of an x and y from the individual x and y values from each data point. By using these sets of data, we are able to solve for b0 and b1. First, you must calculate slope. To solve for b1, you have to square all the individual values of x minus x bar and find the sum of these values. This will be the denominator of b1. In this problem, the denominator is 10. To solve for the numerator of b1, you must multiply all the values of x minus x bar and y minus y bar. The sum of these values will give you the numerator of the slope. In this problem, the numerator calculated to be negative 13. The slope of this problem was negative 1.3, showing that there was a negative line of regression. To solve for the y-intercept, or the b0 variable, you must plug in values into the original linear regression equation. Replace y hat with the mean of the y values, replace the x variable with the mean of the x values, and replace b1 with the slope that was solved for. For my set of values, the mean of y is 5, the mean of x is 3, and the calculated slope is negative 1.3. Now the only unknown variable is b0. Solve for this variable like you would any other algebraic equation to calculate the y-intercept of the line. In this problem, the y-intercept was 8.9. The line of regression for my set of data is y hat is equal to 8.9 minus 1.3x. The other way to solve for the line of regression, which is much simpler, is by using a graphing calculator. Firstly, you press Stat, then Edit. You are then able to enter your x values into L1 and your y values into L2. After that, click Stat again, arrow right to calculate, and scroll down to number 8, which is linear regression for the equation a plus bx. The calculator will present you with the same values of each variable. There are many real-life applications to regression lines. For example, the use of linear regression is especially prominent in business. In business, linear regression models are effective in predicting product sales, understanding inventory levels, and overall supply and demand. This graph shows the estimated revenue generated in the result of a number of advertisements by a company. The independent variable is the amount of ads, and the dependent variable is the amount of money generated. Another real-life example of regression lines in business is to predict future sales of a company based on their historical sales. In this graph, the dependent variable is the amount of future sales. This is reliant on the independent variable, which is the company's previous sales in the past. Finally, this last graph shows the direct and negative correlation between the amount of school days left of online school and how excited I am. The independent variable is the amount of days left in school, and the level of my excitement is the dependent variable. In other words, I'm very excited for school to be over.